Welcome back to my lecture that aspects of biochemical engineering. Now, last couple of lectures I try to concentrate on cell growth kinetics that we discussed the cell growth kinetics both for the batch system and the continuous system. And when we discussed the chemostat process, I told you that we know the continuous start tank reactor. When continuous start tank reactor we use in the biological system, this is we call it chemostat. And major drawback of the chemostat process is the cell mass that is going out of the system. Now, if the rate of cell mass that is going out of the reactor is more as compared to rate of cell mass that is growing in the system, then what will happen is situation will come when there will be no cell present in the reactor. Now, that situation we can overcome by using two different approaches. One is called cell mass recycling, that another we call immobilized whole cell. Now, so today I shall concentrate on that how with the help of cell mass recycling, how we can control the cell mass wasting in your from the system, or the wash out of the cells. Now, first let me explain this, because suppose this is CSTR, and this continuously liquid is coming at a particular flow rate and going out at the particular flow rate. Now, here x0, this is x, and this is also x. Now, what I want to point out that always you will be having cell wastage, what is called F into x. Am I right? So, if this is equal to rate of growth of the cells inside the cell, inside the reactor, then it is fine, because if it is the growth is that that if the rate of growth is same as that, then it is fine. Otherwise, if it is more than that, then the cell concentration will decrease with respect to time. A time will come when there is no cell present in the reactor. Now, another explanation to this process I explained, that is the generation time, because 1 by d is considered as the hydraulic retention time. Now, what is hydraulic retention time means how long you allow a particular liquid resides in the reactor. Now, if your generation time is more than that hydraulic retention time, then what will happen, that your liquid will get less time. So naturally your cells will not grow inside the reactor, and before it grows, you are taking out the liquid from the reactor. That is why we face the situation what we call cell washout. Washout means after some time you will find there is no cell present inside the reactor. This is the major drawback of the chemostat process. Now, this can be overcome. How we can overcome? This can be overcome. Suppose the whatever excess cell mass is going, so if you put a separator here, and we can a part of the cell you are recycling back to the system to maintain the cell mass concentration uniform, then your rate of reaction will be constant. Then there will not be any problem of cell washout. So so we will discuss here the chemostat with cell mass recycling. The chemostat recycling is performed to keep the cell higher than the normal steady state level in a chemostat. So we recycle in a manner so that the cell mass concentration remain constant, higher than that, so that we ensure that your rate of reaction is constant, or more than that we desire. That is, cell recycling increases with the rate of conversion, and obviously that and increases the critical dilution rate for washout, thereby increases the operating flexibility, and can be performed using the centrifuge or settling tank to concentrate biomass leaving the reactor. So, if we see that CSTR, the cell mass recycling system, it basically it looks like this. So, this is rotation, this is like this. So, here we can have the settler, and this is going out. A part of the things you recycle back and part you. So, here what you call cell recycling, this is recycling, and this is called cell wasting. This is called cell wasting, and this is actually the effluent. There is a clear liquid effluent. This is the feed we have. Now, suppose this is the settle cell mass concentration is XU, and this is X. So, when you settle, obviously the cell mass concentration will be more here, and this is the settle cell mass concentration. And let us assume the recycle flow rate is Fr, and this is F0. Okay. Then what will be here? Flow rate F0 plus Fr. Am I right? So, what is the cell that is going out, going in? This, if we assume this is X0, so we can write F0 into X0 plus this is recycling. This is also XU. This is plus Fr into XU. This is equal to what? If X, then plus there will be some production generation. This is plus the rate of growth of the cells inside the system. This is into V. This will be equal to Fr F0 plus Fr into XU X. We can write like this. So, this is by main purpose of recycling. We want to maintain this cell mass concentration uniform or above the certain concentration what we really looking for. Now, this is the process how it can be explained pictorially like this. So, here as I told you, this is the process. This is CSTR. We have continuous start tank reactor or chemostat, and this is the influent, and this is the what is going out, and this is the separator, cell separator concentrated of the cells is there. A part you recycle back. This is the recycle flow rate. This is the settled cell. This is waste recycle flow rate. Yes, we assume here when we carry out, we assume the reaction only take place in the reactor. Reaction doesn't take place in the separator of the pipeline. That is, then we can write the balance equation. So, here all the parameters are noted here that how. But these are different F0, S0 and X0 and all the parameter what there stands for. Now, here the question comes how you can write the balance equation. Let us first consider the cell mass balance across the chemostat, how you can write. I told you what is the input equal to F0 into X0, Fr into Xu. This is Fr into Xu, and this is the input to the cell. And what is the generation that we have? This is the generation V into dx by dt. And what is the output? This is the output. Am I right? Fa is what? Fa is equal to F0 plus Fr. So, this is into X, and plus accumulation under steady state condition. So, since we mentioned the steady state condition, we can assume the rate of accumulation is the 0, and also we can assume that there is no cell death take place. Then what we can write, that alpha equal to Fr by F0, and alpha is considered as the recycle ratio. Alpha is considered as a recycle ratio. So, what is the Fr is equal to what? Alpha into F0. Now, Fa equal to F0 plus Fr. Am I right? Then F0 plus alpha into F0, Fr equal to. So, I can take common F0, I can write 1 plus alpha. This is exactly what is written here. Now, this equation can be modified in this form. This same we have the F0 into X0, Fr is equal to alpha into F0 into Xu, and this is like this F0, this we can modify at F0 into 1 minus 1 plus alpha into X. Then what we can write that we can write now previous equation was like this, and then we can write this is alpha into F0, this is what we have, alpha into F0 and V into F0, and because we considered x0 equal to 0. So, first term we can add that you can neglect, and that is equal to this, and this equation I can write now. We can divide by V both sides, and if you divide by F0 by V equal to what? Dilution rate. So, this we can modify it in this form. Now, now we can assume C equal to XU by C, if you write C equal to XU by X. Now, XU what? Settled cell mass concentration, am I right? And X is the cell mass concentration under in the reactor under steady. So, XU is usually much higher than X. So, I can always say that I can write C always much greater than 1, am I right? So, this is like this, C equal to the concentration ratio of that. Now, we can write XU equal to C into X. Now, this we can write in this form, this XU value we can put C into X. So, this equation can be modified as like this. Now, what is the significance of this equation? Let us try to find out. Now, here I can write mu by D is equal to 1 plus alpha 1 minus C. Okay. Now, what is 1? What is alpha? Alpha is the recycle ratio. Alpha equal to what? FR recycle flow rate by F0, and this usually less than 1, because usually the recycle ratio always should be less than 1. So, let us assume it is 50%, 0.5, let us assume that, and 1 minus, and I told you C always should be greater than 1. So, if we assume this is 2 or 2.5, let us assume that, then what will happen, that 1 plus 0.5 into this will be 1 minus 1.5. 1.5 is how much? This will be after 1 minus 0.75. Am I right? So, this will be 0.25. Now, if it is 0.25, so what I can write? The mu by D equal to 0.25. So, that means that in a CSTR under steady state condition and still mu equal to D, and but here is mu equal to 0.5. That means if you can, if your D by mu is how much? It is 1 by 2.5. That means this is 4. That means that that I can write mu equal to, or I can write D equal to 4 mu. So, I can run this. If you do the recycling, I can run 4 times of the that specific growth of the cells. So, this is the speciality of the recycling of the cells. If you recycling of the cells, how you can justify that we can operate the same system safely. Now, we have already seen that when you plot that xd versus d, that what we have done, we have plotted like this, am I right? And this is the situation that we have here. This is called D washout. And at the same time, we find that here this is what? This is called D max. Now, suppose in case of Baker's fermentation process, we wanted to have maximum amount of cell mass formation. So, what is the maximum cell productivity? Maximum cell productivity is how much? Productivity equal to D max into x. At the D max, what is the x value? That is the maximum. Now, as I told you that D max and D washout, these two, they are very close to each other. So, if you increase a little bit the flow rate, because D equal to what? A by V. Now, if you increase the flow rate little bit high, there is every possibility that D max can meet the D washout situation. Then you will not get any cell mass in the reactor. Now, this system can be safely operated if you recycle the cell. So, even it is increased little bit, it is not going to affect in your system at all. So, this is how we can safeguard the cell washout by recycling of the cells. Then we try to find out that that steady state substrate mass balance across the chemostat. We can write F0, this is F0 into S0, Fr into S, because we assume here this will be S. So, Fr into S, here also it will be S, here also everywhere it will be S, and this is equal to F into, and no generation of the cells, so that will be substrate, this will be 0. This is Fa into S plus that rate of substrate, that is degraded consumption in the system, and rate of accumulation, that should be equal to 0. Now, if you do the analysis of the process like this, we will come across this equation ds0 minus S equal to 1 by x into mu x. So, x will be equal to what? ds0 S mu y x by S. This is cell mass concentration we can easily determine like this. Now, mu, that x equal to this we can you see that we wrote like this, and before that we have derived this equation mu equal to d into 1 minus alpha into 1 minus c. Am I right? So, this I can put it here, and final equation will be this, and thus the biomass increase by a factor of this as compared to the chemostat without recycling. So, this is the comparison that we have made, and then substrate concentration can be obtained by applying monod kinetics is like this. This is the equation that we have, and this already we find this is equal to mu, and monod equation is this, and then we find out the S value will be this, and y value, that x value will be what? Y x by S into S0 minus S. So, if you put the S value here, then you can calculate the value of x. But both S and x value you can calculate with this with the recycling system. Now, if you now you plot this dilution rate with the biomass concentration and the then what we will observe, what we will get, and the rate of biomass formation, both if you get here, then you will find that this is x, this is the two situation we have, R1 and R2. Am I right? What is R1? R1 is the cell mass output per volume without recycling, and R2 is the with the recycling. So, with recycling the cell mass concentration will be like this, and you can see that the washout, d washout is much higher as compared to without recycling. Without recycling it might be close to 1, and it is about 2, and R also R1, that is that cell mass output per without recycling, that has been given here. This is the two situation that we have: rate of cell mass formation in case of without recycling, rate of cell mass formation in case of with recycling. This with recycling our cell mass growth is increased to a great extent. Now, that after here I want to point out one thing, that one thing I point out that we have seen the batch process. Am I right? Batch process, that batch process is like this. So we take the material at a time, allow it to react. After the reaction is over, you take it out. Now, here with respect to time, you can have the cell mass concentration. So, then we can monitor dx by dt. Am I right? So, how we can monitor dx by dt? I told you dx by dt equal to x n plus 1 minus x n minus 1 divided by 2 del t. Am I right? Now, if it is like this, now if you plot x dx by dt versus x, what kind of nature of plot we will get like this. Now, what is the slope? This is 0. Am I right? So, slope is the tan theta is the altitude by base. Am I right? So, it is dx by dt by 1 by x. This is equal to slope. This angle is like this. So, this is nothing but equal to mu, and this mu under steady state condition and sterile feed in case of chemostat, this is equal to d. So, so the batch data that can be possible, from the batch data it is possible to find out that what will be the cell mass concentration in a chemostat at a particular dilution rate, provided you have the plot of dx versus x. Now, if you have this dilution rate, then you can find out the corresponding the cell mass concentration. Now, if you have this much dilution rate, you can find the corresponding. So, without going for this operation of the continuous process, it is possible by simple operation of the batch process is possible to find out the what should be the cell mass concentration in a chemostat. Now, let me explain that how you can analyze the plug flow reactor. It is similar to the plug flow reactor when we discuss during the enzymatic reaction. The analysis of the plug flow reactor per culture follows the same procedure as the enzymatic reaction. The material balance in the section is like this. So, I told you this is kind of tubular flow and plug flow is kind of piston flow. Now, here this this equation is like this, that f is the flow rate and x is the z here, x 0 into z. So, this is z and this is x, this is x z plus x. So, but this is the input, and then rate of growth of the cells, this is the generation of the cells, and then output, and we can assume the consumption, and this we under steady state condition this is equal to 0. Then we can write this equation in this form. This is f into x z plus del z, and x 0 into z, and this equal to, this is the f divided by a is the cross sectional area. If you divide by this, you will get the velocity. Velocity is that into this equal to, now if z equal to tends to 0, then what we can write? This is equal to, we can write that dx by dz, u into dz dz equal to mu into x. Now, if you do the integration, that you know that u, this is the velocity, and dx by x u will to dz. So, this is the reactor that we have. We have a strip here. So, this is dz. Am I right? This the length is dz. Now, we integrate it from 0 to L. This is the L. So, if you integrate that, then we will find L by u. You can bring it here. And this is x 0, they have started with x 0 and finished with x, that is the cell mass concentration. Then we can have this is the L by u, then this is the equation, and L is the what? L by u. L, what is the unit? Is the length. Am I right? Length. And what is the velocity? The unit of u? Length per unit time. So, length will cancel, the time will come. So, L by u is nothing but tau. Am I right? So, this is, we can replace the ln x by x 0 equal to tau. So, we can write the tau, that is the space time of the plug flow reactor, is 1 by mu ln x by x 0. So, this is the same as the expression if you compare with the batch process. The tau plug flow reactor is equal to tau batch process, the same expression that we have. The drawbacks of the plug flow reactor is not suitable for the growth in suspension, because I told you that in the plug flow reactor there is no back mixing. So, if there is a suspended cell, there is every possibility it will settle down, then it is not suitable and can be used recycle or immobilized cell reaction. So, suppose in a column, if you pack the cells in an immobilized column and you pass the substrate here, take out, that is that kind of system we can operate in the plug flow manner. However, the inherent operational problem cannot be avoided, because what is the operation problem? There should not be any back mixing. The difficult to control the temperature and composition variation, because if you here suppose in this reactor, if you make a concentration profile with respect to distance, that is 0, then what will, with respect to distance, at different distance your substrate concentration will be different. So difficult to control the temperature reason is that there is no hesitation, the heat transfer will not be proper, and composition variations of the, I showed you how the composition variations is there. Plug flow maintenance is also more expensive and rarely employed for the industrial purpose. So this is what we have, that plug flow reactor is rarely used. Now, comparison between the major mode of cultivation, what I lastly pointed out, the kinetic characteristics of plug flow reactor same as batch process, large number of CSTR connected in series, conversion characteristics approaches to those of plug flow reactor. I showed you that when you plot minus RA versus CA in the chemical reaction, I showed you if you have this in case of product, this is in case of product inhibition, we go for this is tau plug flow reactor. Am I right? Now this can be, but in case of CSTR it will be area is more, but this can be replaced by multiple CSTR like this. So you have multiple CSTR. This can be large number of CSTR connected in series. The conversion characteristics approaches to the batch and plug flow reactor. The rate of conversion of chemostat operation Dmax in 10 to 20 times greater than plug flow reactor and or batch process. For the most fermentation, the CSTR offers significant theoretical advantage over the other nodes of reactor operation. They can be very easily operated. A simple start tank reactor, you pass your substrate one and take out product other end. However, despite the benefit of CSTR, majority of the commercial fermentation is conducted in the batch mode, because the always continuous process requires some kind of skill of operation, and batch fermentation is lower risk of contamination as compared to CSTR. This we already pointed out, that CSTR when you operate for long time there will be some kind of contamination problem, and whereas in case of batch system the contamination problem comparatively will be very less. Equipment and control failure during the long term operations are associated with the problem with the CSTR. So, and this is basically the instrumental controls. So, if then any kind of instrumentation failure is there, then the process is going to suffer. So, these are the several problems we face during the operation of CSTR. So, what I try to point out here that the major problem that we have with the chemostat process is the cell mass wasting from the reactor, and that can be and meeting the situation like cell washout, and that problem can be easily overcome if we recycle the cell in the solid matrix and recycle the cell in the particular reactor. And later on we find that how we can determine the space time that is required in the plug flow reactor, and finally we make a clear cut the difference between the chemostat and the plug flow reactor of the batch process. And what I pointed out, that batch process contamination problem will be less, but productivity will be more in case of CSTR, and plug flow reactor will be very difficult to operate. Thank you very much.